Hey everyone, Ryan DeGregorio here, Stargazing Leader for Wyoming Stargazing. Thanks for joining me, and welcome to Mind Bending Astronomy. In every episode, we share with you a mind-bending fact about astronomy. Last time, Sam introduced us to the concepts of string theory. Today, I'm going to delve into the finer details and implications of this theory. Now, if you recall, the standard model of physics right now can't be called complete because it does not include gravity. In the standard model, each of the four fundamental forces is mediated by a force-carrying particle called a force carrier. Photons are probably the particles you're most familiar with. They're just light, visible, ultraviolet, infrared, microwaves, radio waves, all the same thing. They're all light. And they are the force carriers for electromagnetism. Now, gluons are the force carriers of the strong nuclear force. They are responsible for keeping photons and neutrons stuck together like glue. W and Z bosons are the force carriers of the weak nuclear force, responsible for things like radioactive decay. And then finally, we've proposed a hypothetical particle called a graviton, which has yet to be discovered, that would mediate the force of gravity. As far as we know, these particles are point-like. They don't really have a real size or cross-sectional area. They're just like little dots of incomprehensible smallness. Now, string theory may be able to accommodate for gravity among the rest of these particles. Here's how it would work. Instead of the universe being made up of points, let's say that it's made up of something slightly more complex, lines or strings. So now, instead of everything being a point-like particle, everything in the universe is just a string vibrating at a different frequency. Just like vibrating strings at different frequencies on a guitar give you different notes. A string vibrating in one way may be a quark, but another string vibrating a little differently may be a photon. Using strings, we could describe gravity in the same way we describe the subatomic particles. At last, we could merge the relativistic world of the very big with the quantum world of the very small. But it's not that simple. String theory requires a lot of other conditions for it to be considered a theory for everything. For one, our universe operates in 4 dimensions. There are 3 spatial, length, width, and depth, and 1 temporal or time dimension, or just duration. Now, if all the mathematics involved in string theory are to work out, it needs 10 dimensions. String theory only works in 10 dimensions. That's a little bit tricky to think about. In the transcript, I've linked a pretty helpful video, I think. Another problem with string theory is that there are an infinite number of ways you can vibrate a string, but there are only a handful of different kinds of particles. What could be the explanation for why there are not infinitely more particles? And if there are, what would cause them to break down or be unobservable? And then finally, and most importantly, the theory of strings needs to be testable for it to be a valid idea. But right now, it's almost impossible to come up with an experiment that gives any merit to string theory. Predictions from string theory have yet to be verified experimentally. So it can't currently be proven wrong either. So science is just a way of thinking about things. It works by upholding explanations that fit our observations and that are simple, and disregarding those that don't fit as well. So string theory, like general relativity and quantum mechanics, is just another idea. A brilliant idea, but just an idea. We're still searching for that theory that can explain everything we can observe.